Hello everyone. I would first off like to thank each and every one of you for being in attendance for my capstone presentation. I've put in a lot of work throughout the year and I'm excited to present to you all what I've accomplished. So without further ado, let's get started into Ruda, Custom Drone Technologies, my capstone in computer science. A little bit about me first. My name is Ruda Goel. I am a senior here at Grandview High School. I'm involved in a bunch of different clubs like TSA, FBLA, and a bunch of performing arts groups like marching band and jazz ensemble. Speaking more towards my academics, I've achieved a CSWP in mechanical design, so I kind of know my way around SolidWorks and just CAD models. And then finally, I'll be attending Georgia Tech this fall for studying electrical and computer engineering. In today's presentation, we're going to go over 6 major items. We're going to cover some basic project overview stuff like goals and objectives. Then we're going to dive into my advisory team, and then into my timeline. And then we're going to actually get into the core of my project with the electrical circuit. And then finally, we're going to finish off with the frame and my future steps. So the first part of this project started off really with the inspiration. Well, one, I was bummed out by the physics E&M curriculum because I thought we would get into computer hardware, but that's not really what happened. Second thing, I also really like just ripping open any electronics, take old TV remote controllers, or last summer I broke apart a microwave and it was a really fun experience. So yeah, I wanted to apply that this year. And then drones, once again, are just extremely cool, right? So I wanted to take the two and combine it and just make a drone. So what the actual project is I wanted to design and manufacture a quadcopter drone system from complete scratch. What this really means is I wanted to design the electrical circuitry from the ground up. I also wanted to write the code base completely from scratch. And I wanted to design the frame, and I wanted to do a bunch of analysis and simulations, making sure it's the best model I could get it working. And I had 5 main objectives for my project. Number 1, I wanted to do both electronics and mechanical systems into one. I also wanted to just learn more about SolidWorks and a bunch of circuit software like EasyEDA. And I also wanted to just spend a year researching a new topic, something especially that I was going to major in this fall, and just present my research in a portfolio. Scheduling, I also wanted to create a timeline for a project this big and chunk it out, see really if I could do it over the course of a year. And finally, I just wanted to create a research portfolio I could share out to universities. And so my company logo, as you can see, I really dramatized the whole idea of an electrical circuit and a design, because that's what my project is. I really wanted to design the electrical circuit from the ground up, and I really believe my logo shows that. For the namesake, it actually comes from Hindu mythology. There's a character, there's a huge antagonist character, his name is Ravan, and he has a flying machine. So I thought, quadcopter, flying machine, combine the two. Props off to Tron for helping me come up with that name. And then the color scheme, I chose a lot of blue and black just to evoke ideas of innovation and professionalism. Now, on with my advisory team, I have one expert advisor. Her name is Amrita Mathuria. She's currently out of Oregon. And one thing I want to highlight is that she has over 100 patents for just research into supercomputers and ideas of how can we change up circuitry so that it's for supercomputer optimization, for example, like cosmological models. Also, she was a developer in a recent startup for drones called CrazyFly, so having her input was really, really crucial. And then no advisory team is complete without my support advisors. I have number 1, Dylan Gross. He is my expert in mechanical design. Then I have Wesley Walker, who I can just go to for anything related to physics. And then I have Sharon Belair, who's just a programming nerd. Then I also have Bryce Robichaud, who helps me with the circuit software, and he's a cool guy to talk to. And then finally, we have Ryan Fritchell, who helped me with a lot of the flow simulations. Now, what you'll notice in my project timeline is it's a lot of a game of just expectation versus reality. Back in September and October, I used to be a spirited, free young man who believed I could accomplish almost God knows what in the span of 6 months. That's not the case, right? I believed that I could accomplish most of my research within 2 weeks. Little did I know that was completely wrong. I had to chunk out my second phase, which was actually designing the circuit, and I had to add a whole other section of research, right? And it just gets even worse for phase 3 and phase 4, where I completely derail, right? Throughout the course of all this year, I had to invent so much research because I didn't know anything about this kind of stuff, right? I had no pre-existing knowledge of classes, so I had to really study from the ground up. And overall, my research was, I would say, around 10 weeks, right? Now, if you couple that with all of the other different designs, like mechanical design and the code base, you can really see that I pushed everything behind just to understand what was going on. And in the end, I do believe it was worth it to adjust my timeline. Yeah, a lot of adjustments. So here's where we really get into the critical aspects of my project. I'm first going to walk through the electrical circuit design. Now, before we get started, I wanted to highlight some things. A printed circuit board is actually like common misconception. It's actually just this green board with a bunch of wires connecting all the different components together. The reason a lot of people get it confused is because they see all of these different components on, but really what the printed circuit board is it's just a compact way of connecting everything, right? Then you have the flight controller, which is actually the brains of what would be on a quadcopter. And then finally, you have like a microcontroller, which is basically the computer on a chip, right? That's what almost all smart devices use as the core processing unit. Now, my base design and research went off of one flight controller that I had. Last summer, when I ripped apart that microwave, I also ripped apart one drone. And at the center, I found this flight controller. So all of my design and research really was based on this. Like, if I know this is a trusted device, then what can I find in my research that actually helps me? And I found three main items that you need in any electrical circuit. Number one, you need the microcontroller. Like I said, the computer on a chip. You also need something called a crystal oscillator, which is basically just a unit for telling time. And then finally, you needed an inertial measurement unit. It's a sensor that allows the drone to measure where it is in relation to Earth's gravity and how fast it's spinning. So I needed these three things. But once I got these three things, I was wondering, how do I actually connect them? Like, I know they exist, and I know that they're supposed to be connected, but how do I actually go about doing that? And what I did reference was the data sheet. There's this international standard that anytime a chip is made, you have to release a data sheet. For my microcontroller, it's around like 700 pages. And once I actually got into it, it was really, really daunting because these microcontroller data sheets can get really, really complex. And so after like almost 5 months of just digging my head in these, I am finally able to understand what's going on. And so the reason I included this in my presentation is because this was probably the cornerstone of all my research. So I took all of that information and I finally compiled my first schematic. Right, as you can see, I have the microcontroller in the center and all the peripheral components to the side. And then I hopped onto the circuit design software where I just really loved sitting at my computer and layering everything together. It took almost 10 hours. And then finally, I have the shipment in real life. And if you'd like to come take a closer look, you are welcome to do so at my table. But here it is. And I did a very similar approach for my remote controller module. I hopped on the schematics. Then I did even more sitting at my desk with fun and placing it all onto one circuit board, and I have a final version. If you take a close look in the center, you'll see this microcontroller that I soldered on. And the size of these microcontroller pins are extremely small, so I just want you guys to appreciate my soldering in action, right? I spent almost 20 hours in just the past month just soldering, right? And my room turned into something that like should not happen. But essentially, this is where I come into my first challenge, and it's the whole practice of soldering, right? That's my finger for reference, and that is the actual microcontroller, right? The pins are so incredibly small that soldering each one by hand is not feasible. On top of that, I do not have a good soldering iron, right? So what really happened in the end is when I soldered on the microcontroller for this printed circuit board, I completely fried the chip. Right? One of the connections were bridged, and I passed current where it wasn't supposed to be, and it got ruined. So then I opted to come up with the next solution, which was using the Arduino Nano. This is a professionally built microchip, and essentially what it is, it still has a microcontroller in the center, but it's basically put on by a fab lab somewhere in wherever it's manufactured. And I thought this was the best idea because I can interact with these pins in the easiest way possible. So then I hopped on to my circuit design for version 2. Then I hopped onto this circuit board design software. And then finally, I have my working circuit that is on my drone. And I followed a very similar approach once again for my remote controller module. This time, I'm using the Arduino Uno. And if you would like to see that model, you are more than welcome to come to my table. I'd love to show it off. But once we actually have the flight controller developed, we have to go about controlling the motors, right? Like once you have the brains, how do you actually tell it to fly? And the main thing to do is we have to control the speeds of the motors. And through my research, I found that the best way to do it is by adjusting the voltages. When you have 0 volts applied, you're going to get no speed intuitively. And once you have max voltage, you're obviously going to get max speed. And so with this in mind, it's really easy to control the motors mechanically, right? Like we all know what variable resistors are, and we have a little dial that you can use to control voltage. But how do you do that actually digitally? Because I'm not going to be sitting on the drone like adjusting the speed of the motors. And through some more research, I found that it's through pulse width modulation, or PWM techniques. Essentially, it's a way for the flight controller to switch back and forth between really high and really low voltages, giving different speeds. So with that in mind, I finally was able to control the speeds of the motors. And I have these different pins connected to my motors from the flight controller. But that's where I run into my second challenge, where the motors were not being able to supply, where the motors were not supplied enough current, right? If I was able to adjust the speed of the motors to the voltage, my microcontroller wasn't able to adjust the current, right? To put that in perspective, the current that a motor needs is around 2.7 amps, or 2700 milliamps. My Arduino can only output 7, right? I need 400 times more current, which is practically impossible. I'm not going to buy 400 microcontrollers, right? That's not how it's going to work. So I did some more research, and I uncovered that the next solution was to use a MOSFET. It's a special type of transistor that allows me to switch voltage back and forth between really, really intense batteries, right? So if you would like to know the mechanics of how I wired it in my circuit, I would love to explain it at my table, but I think it's a little too time-consuming for this presentation. But just know that I was able to wire the MOSFET in series with my motor, and it was finally able to work. But when I wired that in series and when I actually had it all planned out, when I tested it in theory, I ran into another challenge. And I believe this challenge is best explained through like an interactive game with the audience. Okay? So do we all know how to play Spot the Difference? Yeah? Yeah. Okay. Can we spot the difference between these two?
The logo.
Exactly, the logo, right? You're completely right. All right, let's get into a second example. It's a little bit harder. It's extremely hard.
Number pins.
Not the pins. No, there's still 2 pins here.
Rods.
Nope. Guys, let me save you the trouble, okay? We are missing 1 crystal oscillator there. Come on, you guys gonna figure that out? It took me almost like 2 months to figure that out, and I was ready to like punch my computer. And the main reason I'm showing you guys this is because on the internet there exists so many clones of our electronics. So instead of trying to cheap out for $3 on buying cheaper electronics, don't ever do that. Because in the previous examples, these different clones actually have different software running on them. So that's why it can make it almost insanely hard, right? And so I fell trapped to that 3 different times. One with the programmer, second with my Bluetooth module, and finally with my MOSFET. As I said before, I used this as a solution, but I got scammed out between a P channel and an N channel. So in the end, my flight controller isn't exactly how it's supposed to work. But I figured out another solution, right? I was debating with my dad for almost a long time, and I drew up the solution, actually on the back of my AP Lit essays. And the solution actually is to use 5 batteries all taped together. So it looks kind of like messy now, but this is the solution that I was able to come up with in this context, right? This is obviously not the preferred solution because you've never seen a drone ever looking like this. But the reason it works is because the special type of MOSFET that I used works with this method. It's not preferred, but it works. Okay, and this is where I arrived at my final version 2 prototype. All right, now I really want to get into the mechanical frame, the actual physical design, which I think is even better. So I hopped onto SolidWorks after like a bunch of research. This took me almost 15 hours to do. It's just a version 1 model. But then for this model, I really wanted to focus on 2 main things: weight optimization and the use of this guardrail system to protect the propellers. Because I've seen a lot of videos where the propellers just completely fly off. In terms of weight reduction, I was able to spot reduce a bunch of the weight on the arms. And don't say that this lost any structural integrity, because I performed a stress test analysis with 20 newtons, and the max deformation was around 5 micrometers, which is practically invisible to the human eye. SolidWorks is just really, really dramatic when it comes to like stress tests. And so one key piece of research that I wanted to mention is that the direction of rotation for propellers. if you'll notice, on my design, I have the diagonals colored together, meaning that they're rotating in the same direction. In other words, the purple propellers are rotating in a counterclockwise direction, while the green ones are rotating in a clockwise. Now the reason for this, there's a lot of physics involved, but the main gist of it is because when you spin them all in the same direction, you're gonna have your drone start spinning, which you don't want at all, right? When you start spinning them in opposite directions, you get a zero resultant torque. And into the propellers, this was probably the core of my research and a lot of time where I spent because of just how the airfoil is shaped, right? In SolidWorks, I do have my certification in surfacing, but it really, really tested my limits because of just how many dimensions I had to put and how many dimensions I had to guess on for this, right? But in the end, my propellers were able to create a good enough cut angle such that it cuts enough air to generate enough thrust. If you'd like to know more about the mechanics, I would love to talk about it at my table presentation because there's actually a lot of math that goes into it and how it creates a difference in pressure and how it can actually generate it. But my propellers also encountered a huge challenge. In this really, really cool spinning GIF, you can see that there's a lot of curvature in my drones, right? There should not be that many colors when a 3D printer is involved, right? And when that actually happens, your 3D printer starts to cry a lot, right? A lot of the supports just didn't break off. And if you actually feel at my table the propellers, it feels like sandpaper, which it should not feel like. So then I hopped on some more research, and then I kind of went through some more iterations, and I came into a lucky solution. The printers at the school are actually really, really good at this. I was able to print like really close to 4 or even 2 layer lines, which is extremely thin for my propellers. Like I can almost bend this stuff, right? And the whole reason that it is good is because 1, it's really light, so my motors can spin it, and 2, it's just a better and smoother shape overall. So that way the air can cut it better. Now this is a final version 2 assembly of my drone frame. And one of the advantages that I capitalize on is the fact that it's 1 unit, that it has a really small drag coefficient, and it has increased strength overall. And here I did a bunch of flow simulations with the help of Ryan. And I was able to figure out that my drag coefficient in my version 2 prototype was significantly reduced than in my version 1, just because of all the holes that are involved. And so my final pitfall was when I actually combined the two together, right? Like I mentioned this before, but this is my final working model of the drone. It is extremely heavy, right? And the propellers themselves cannot lift up the drone. But what I was able to do was I was able to prove that the circuit works. To give it to you in numbers, this drone weighs around 151 grams, when in reality it should weigh around 75. Because each motor provides around 50 grams of thrust, the motors in total should be able to lift twice its body weight. That's just not possible with this current scenario, but I do have potential solutions. Number 1, I can use the correct MOSFET and not get cheaped out by electronics this time, or I can just change the design of my motors and get beefier motors and change the design of my propellers. In either cases, it's going to generate more thrust and lift the drone. So before I wrap up today, I want to just leave off with a brief project summary. Major project accomplishments were 1, I was able to research a bunch into microcontrollers and integrated circuits and learn a lot about them. Then I was able to really control the design of the whole quadcopter from the ground up. And I was able to do a bunch of analysis that I couldn't have been able to do otherwise. And finally, I was able to learn how quadcopters work overall. Now, thinking more towards the future is the stabilization. If the drone were to actually fly, I would want it to be able to hover first. Now, the way that you go about doing this is by first you take all the data from the inertial measurement unit, or how it's positioned, both the gyroscope and the accelerometer. Then you pass that through a bunch of mathematical models called data filtering, right? To filter out the bad data from the good data, and then you're actually able to control each individual motor. Now, what I want to focus on is the data filtering, because that research took me all the way up until here, right? The data filter is actually really necessary, because if you look on this graph, the constant data is really small, but once you turn on the motor, the vibrations alone from the motor can cause the data to skew so much, right? And so we start to have 2 different sets of data. We have measurements from our sensor, which already include really bad inaccuracies, and then we also have a predicted state of the drone. And those imperfections are caused by a bunch of vibrations, right? So we have these 2 different measurements, and we don't know which one to trust more, right? But luckily, there was a guy named Kalman who invented a mathematical model that was able to take both of these data sets and figure out what to actually do with them. So once we pass these through data sets into the Kalman filter, we finally get a good answer that we can use in our next calculations. Yeah. And this is the Kalman filter. If you actually look at it graphically, what it does is it takes an initial state, then it takes the predicted state, and then it actually computes like what the final trusted state solution should be in the end. Yeah, and so before I actually close off today, I want to make some final remarks that this class overall has been really, really beneficial for me. I've loved every process through it, and I really, really recommend any individual who's interested in STEM to take these classes overall. I've learned a lot, and yeah, I would take it again in the future. So, any questions? And thank you for listening to my presentation. Yeah, Dylan.
What was your favorite part about this project?
Ooh. My favorite part was definitely seeing all the motors spin and being able to control it. That was so much satisfaction, almost like 4 months of just like in one moment. That was my best moment. Yes, Matt.
So you said the microchip data sheet you found online is like about 700 pages.
Yes.
How did you just go about digesting all that information
Ooh.
and like organizing it
Okay.
efficiently?
So it's pretty common knowledge that a lot of these microchips, they come from China, right? They're manufactured by Chinese companies. So these companies are actually really beneficial. They give out videos on how to interpret these data sheets. But the problem is, a bunch of them were not in English. They were in Mandarin. So I had to use the closed captions and actually read through a bunch of just like YouTube videos of how to interpret this. But like slowly but surely, I was able to read it after 5 months. Yes, Lou.
You mentioned that you took off a bunch of weight in your SolidWorks design. Could you walk me through how you did that?
Yeah, for sure. Let me go back. Okay. Yeah, okay. So I noticed that there was a bunch of just like nonsense plastic that was in the way of connecting these arms together, right? So this was definitely just like a hypothetical solution, but I thought like, what if I take the weight out of these components, right? And what I first thought is rather than taking it out from the top, I thought I was going to drill holes from the side. And I did a stress test with that and it broke within like 5 units, right? So then I tried it from the top and it actually worked out way better than I thought. So it's just a bunch of like trial and error that I got there. Yes?
How do you control yaw without affecting your overall thrust for your altitude?
Or control yaw without... Sorry, can you repeat the question?
How do you control yaw? So you're rotating your drum without affecting your overall thrust, so it affects your altitude.
So I'm not sure exactly how to control yaw. I know how to control the roll and the pitch by controlling all 4 motors. But I would almost imagine that because these motors spin in opposite directions, I would almost imagine that you would reduce the speeds just slightly of one of these motors so that like the clockwise directions would start spinning faster, and that's how you would generate the yaw.
So you offset the green for the blue for yaw.
Any other questions? Yes, Casey.
Do you plan to continue this project after this class?
Yes, I really want to reduce it down to 1 battery, and I want to just see if we can get off the ground. So, yeah, I do it. Yes, Ryan.
How important is like the center of mass being in the center of the drum?
Oh, it's absolutely integral, right? Because if your center of mass is off, you first have to calculate how much it's off by, and then you have to use all of that in your measurements when you like, take all the gyroscope data, take all the accelerometer data, because that's where you're essentially measuring all the data from. Any questions? Yes, Yusuf.
In what ways did your advisor contribute to the project?
Yeah, so a lot of my questions were way too specific for her to answer just in this project. So her experience in Crazy Fly, that drone startup, she pointed me actually towards the right area of research of where I should like figure out my question, right? Because there's a bunch of different sources of where I could search up, but actually pointing me in the right direction was a major help because it helped me reduce down a bunch of the information.
And what was your overall cost?
Oh, it was around $250. Yeah. Yeah, Sergeant.
So before you like started your project, did you know stuff about like circuit boards and controls?
So I had an Arduino kit beforehand, but my knowledge on it was really bad, right? I practically knew nothing about the actual circuit boards, so I had to spend a bunch of time just researching what's going on. Yes?
How did you find the motivation to be going for 4 months?
Oh, my grade. No, but also like I really just didn't want to give up because that would have been like lame. Like being the only kid in the class, well, not the only kid, but being the kid in the class to give up is pretty a lame thing to have labeled on you. Yeah, so that public embarrassment is what set me right. Cool.